we assume the material is still very linear, like ceramic or carbon. So for most of linear elastic material, there is a theoretical strength for it, but most of the time you haven't reached that point, then you failed because there's some other things happen, which like brittle fracture. So you release your energy much earlier than that point. And a typical example for that is a crack in a metal. For a relative brittle metal, that means some of the metal has some carbon content inside to make it much stronger, but at the same time reduce its toughness, so become very brittle. So brittle material, as I said, ceramics, carbon. For some ductile material, we can still think it as a linear elastic as long as the plastic deformation, for example, at that crack tip, is restricted to the vicinity of the crack tip. So it's not grow hugely like that, but it's limited in the small region. It's still like a linear elastic material. Okay. And there's a lot of fractal modes, but generally they can classify it into 3 modes. So mode 1, basically you open the crack, okay? You open the crack, so for example, you have a piece of paper, you open the crack. In basically loading a case like uniaxially on that 2 direction, like double cantilever beam, you're doing that. And mode 2, you apply a shear loading. So you open the crack in a shear mode. But mode 3, which is out of plane shear, so you're tearing the crack, like you're tearing your paper. Mostly you're doing that if you don't like your material. So now I want to ask someone to help me to break some aluminium foil. So I need 3 volunteers or 4. Anyone want to come here just one by one? That one? Really? Just because I want to show everyone from the screen so everyone can see the... Okay. Come if you want, yeah. I need volunteer, okay? So there's 4 pieces of aluminium. So that's the first one. If you want to do that, this is the aluminium, and there's no notch yet. So it's a perfect aluminium foil. Now just break it. Try your best. If you can stretch it. Yeah, just apply uniaxial loading. I know you couldn't. and do the second one. So now do this one. So just let everyone to see what's happened here. Now you have a circular hole inside of that. It's very quick, right? Yeah. So there's some stress concentration if you look at that, and at that notch. So basically, you are breaking that because you have less material to hold your load. Okay. So come and do another one. So actually, I make this hole. Yeah, do that way. So actually, just be careful. Slowly, yeah. Yeah. So you can see actually the blunting of the hole at that crack tip, and eventually start break. So still, aluminium supposed to be very plastic, but actually in this case it still looks very brittle. Go ahead. And there's another one, actually, I cut a notch here, if you can see here, a very sharp notch. And now you can try to break it. Yeah, much easier. So kind of you can feel the difficulty to break the material. So the hardest one is the one without any notch, and then the one with the circular, and the one with the ellipse. And the final one is the very sharp one. Okay, thank you very much. Yeah. So just give you the idea of how a notch can make a fracture happen so easily. So I know most of the people love to eating some crepes. Okay. I'm not let you to eat it right now. You can eat it afterward, but the idea is for most of your packaging, okay, when you buy any kind of food, they must have a notch. But unfortunately for these crepes, there's no notch at all. They force you to open from that direction. I don't want to do that. So most of the packaging, they must have a notch, something like that. I just cut it for you. Okay. So this should have a notch like that. Did you see that? Okay. But unfortunately, is with that notch is much easier to open that, right? Okay. That's crepes. You can enjoy it afterwards. So just give the idea of the notch, the why you need to create a notch in some of the scenario. Okay. Let's go back to the slides. So stress concentration. So doing this like a practical experiment in the class, just to give you the idea of the stress concentration. Here you're looking at an ellipse hole here. So with a width of 2a here, with a height of 2b, and the radius here is rho. So basically, you're applying a uniaction loading remotely. So remotely, I mean the hole is far away from the loading point. So that means the stress eventually will very uniform along here. And Ingalls, who is from Cambridge, I think, he actually derived stress concentration 100 years before. So it's a very old equation, but still valid. So basically, he worked out the stress along that point, A, equivalent to the remote stress, sigma infinite. Doesn't mean the stress is infinite large, but it just means it's very far away from your hole. But that remote stress times 1 plus the aspect ratio, basically, roughly, 2A over B. So that's the equation to give that idea. So what happens if it is a circular hole? That means A equal to B, right? So in that case, A equal to B, then this sigma max, so equal to 1 plus 2. So give you 3 sigma remote stress. So if you look at the stress concentration, so some of the volunteers have done that. So basically, you have the stress concentration along that area. So imagine like you have less material to hold the full load. So that means only this piece and this piece of the material sustain the load. So that stress along that tip will give you like 3 sigma remote. Okay? So that's the relation for the circular hole. And if you do some final element calculation, so you can see actually this part undergo a very huge tensile stress on these two. They are basically under tensile loading if you draw that. And this part, because the Poisson ratio effect, some of the material under compressive loading from here and from here. So that's why you have a compressive stress. Now, if you make this circular shape a bit more like this ellipse, so what happens for that? So for this ellipse, it will give a more general equation like that. But now, if I really narrow down this hole from 2B, now I just make it just a line, so very sharp crack tip, which looks like that, and the volunteer has done that as well. So now you cut a very sharp tip along that, and you can assume that it's very, very small in that tip. So in that case, what happens is this round B is equal to 0, not infinite, sorry. So in that case, B equal to 0, and this term, it becomes infinite. Okay? Hugely increase that stress concentration at that point. So in that case, you can draw the stress at that tip. So the stress closing to that tip will be infinite. So you couldn't quantify that, basically. And if you go along that crack tip, you will gradually reduce that in a relationship at that. Okay? So that gives you, the sharper the tip you created, the higher the stress concentrated at that tip. So that easily will help you break your material. Okay? So that's why I point here is sigma max equal to infinite. So I know when I send you these slides, people will get a bit scared why there's so many complicated equations here. But here is just to let you understand why, but not ask you to remember it. So for a very sharp crack tip, okay, people has developed more accurate solution for that stress distribution rather than the Ingalls one. So the analytic solution still the approximate solution, because they have removed some high order term. It looks like if you draw that in a polar coordinate system, so you have a piece of a material in the space around here, and this distance from this material to your crack tip is r, and there's an angle here is theta. So that kind of relationship, if you derive the stress field for that piece of material, it will give you this equation, sigma xs, which will relate to this angle theta, and also we will relate you to this crack length A, and R1 is the distance here. So just forget the 1 term here, just some equation I copied from the book. And just give you the idea, like it is relevant to your remote stress, sigma 0 here, using the different, but it's the same idea of remote stress. So just forget the whole term, doesn't matter. But what happens if you let the theta equal to 0? So this term, theta equal to 0, and this term will equal to 1, and this whole term will equal to 0. And the whole term will simplify to the equation like that. sigma xx equal to sigma yy equal to this equation. Here, I just times a pi here on top and bottom, so give you this equation. And so what that means, I just want to relate the stress in that point to the remote stress, because I couldn't measure that in my experiment. That's some calculation or prediction stress. So I don't know this R, what that means, and this A is the defined crack length. Now, if you actually define a new parameter, which I already introduced that in the first lecture, which is called stress intensity factor. So from 1957, Irwin found actually there's a parameter called stress intensity factor K, which you can define that K can be related to that crack tip stress sigma yy with a term square root 2 pi x. X can be related to that crack length. So let me show you. So x can be anywhere here, the position. And so Ki is the parameter he introduced. So when you compare the equation we derived before, the only difference is actually at the crack tip. So the bottom part is the same. If you assume x equal to R1 in any of the position, the only difference is the top part. So people will ask what the actual meaning of the Ki. So actual meaning is the Ki equal to the top part. Okay? So this two comparison, I mean, here to give you the definition of the Ki, stress intensity factor, which equal to the remote stress times square root of pi times the crack length. So that's something more easy to use for most of the case, because you know this sigma 0 from your loading that you applied, and you know the notch length A that you cut, right? And then you know this stress intensity factor at the crack tip. And the unit for this factor is very weird, but think about the stress unit is megpa, and think about the length here. So it's meter for your crack length. So it's megpa square root of meter. So that's the unit of this Ki. Okay? Now, when we rewrite the equation before, so we can, this term is the same as before, and we just replace the top part with Ki. So that's how you relate that stress at any point of here to this equation. Okay? And if you plot that, again, it's very similar to the one you saw before. And it will be very large or infinite if you close to this crack tip, and it will decrease if you look at the material far from the crack tip. Okay, this is the notch you cut. So that gives you the understanding of the, yeah, almost there. So now let's look at some stress which can, in the typical situation, we have different samples. Some of the one are looking at that, which we call single notch specimen. You load it just when you cut a single notch on one side. And most general case is you have a central notch like that, and you cut it in the center. So most of the stress intensity factor you can define like this. sigma remote stress times the square root pi a. But there is one scale factor which we call geometric correction factor y. So which normally you do that because remember all the analytic solution is an approximation. It's not the real calculation. So people actually get the exact solution for that from the finite element. And then they calibrate when you define different crack lengths, A, different load, then you get these Y parameters, which most of the case is close to 1. But some of the case, like for this case, 1.122, and for this case, I would say you can say just equal to 1. And just give you the idea, if you see something like a Y in front of here, that's just a constant, which people will give you from other calculation, like finite elements. Okay? So, I think let's just stop here and have a break. Okay? Okay, let's go back to the fracture toughness part. So before we are talking about this stress intensity factor, but now I give you another value called fracture toughness. What the relation between them? Actually, fracture toughness is a critical value of stress intensity factor. So once you keep applying your loading, increase your stress, and your stress intensity factor will also increase until you reach a critical value. At that value, the material will start to fracture, so the crack will start to grow. So that value is called fracture toughness. It characterizes the material properties, basically how strong it is to resist the fracture. So if you look at here, this equation is similar like the stress intensity factor. The only thing difference is now the remote stress will have a critical value such that the material will have the cracking happen. Okay, that's the definition. So it's actually called material constant. So you can think about strength and stress. So stress is a general stress, but there is a critical point the material will fail. That is strength. Similarly here. So the material will fracture at the critical point of fracture toughness, or stress intensity factor. So how we can measure this value? So most people will ask. We measure that from experiment. I will show you later. So some questions I want to ask you. So maybe you have seen in my previous slides, we often use 2A to define the crack length for a typical central crack panel. So why we define a 2A rather than A for that scenario? And we define A for a single side notch specimen. Let me show you that graph. So you see here, I define A for this scenario. I define 2A for this part. So just imagine there's a crack start to grow. Because it's a symmetric problem, it will grow in both sides. Grow from this side and grow from that side. So that's why to make our life easier for calculation, most of the time we define 2A. Otherwise, you always need to remember, divide your total length by 2. For this type of case, you just think about A. is enough. But this one, you need to cut them into 2 pieces and think about that only half of the crack length will generate that stress concentration on the tip. Okay? So most of my definition for this fracture phenomenon is by using 2A, a double that. But when you look at the equation, K, there's only A here, right? Because you need to think about half of them are doing the job. Okay, that's first question. The second question is why we use fracture toughness instead of stress to predict the crack growth. Again, look at the equation. If we just think about the crack is determined by the strength, it's not enough. You need to think about the crack length, initial crack length as well. So by using the stress intensity factor, you accounting both of them, the stress and the crack length. That's why we need to cut a notch in your specimen. Okay? That's the answer. And how to measure the fracture toughness? We know how to measure the dog-bound specimen to measure the yield strength. Just apply uniaxial loading on the specimen. But how to measure the fracture toughness? Think about that. And again, look at the equation. You need to think about the stress, remote stress you applied. You need to think about the crack length again in that scenario. So in our test, we need to measure both of them to give you a stress intensity factor. And until that point, when the material starts to fracture, then that's the critical point, and that's the value for the fracture toughness. Okay? That's how you measure it. So let me show you some typical example to measure the fracture toughness. So one configuration, which is called compact tension. Compact tension, compact means the specimen here is very small. It's very compact. Because using that configuration, you have a 2 pinhole here. And when you load that 2 pinhole from upside and downside, and you can manage to apply a stress very localized at that crack tip. By doing that, you can easily break the specimen, much easier than we do for the central crack panel. So you are familiar with this image in the QM+. So basically, that is compact tension test. You have 2 pinhole here, and you put that in your mechanical testing machine, and you are loading them together. Then you actually open the crack gradually, so you can see how sharp it is when you propagate the crack. Similarly, you can do this another type of configuration, which is like that. If you look at here, there's 1 point, 2, 3. There's 3 points here. We call it 3-point bending configuration. By doing that, you apply a load from here, and there's another point as a roller to support the specimen. And now this is the actual test. Now the pin from the bottom side is reversed, or just you can imagine the image is rotated 180 degrees. So the pin here is downward to load the specimen. There's another 2 pin here. So imagine now, for a bending specimen, the bottom, what kind of stress state it's taking? Tension or compression? So imagine a fiber here. It is stretched or compressed. I can hear someone is saying stretched. You're right. So because in that case, the bending specimen in the bottom side is under stretching, so it's under tension. So you're actually applying mode 1 open loading, similar like the compact tension. You open the crack, basically as a mode 1 fracture. By mode 1, I said, I'm showing you the crack mode in 3 modes. That is, mode 1 is the open mode, open the crack. Mode 2 is the shear mode, shearing the crack, okay? And mode 3 is the tearing. And here I want to show you the actual test I did for carbon epoxy composite. So they are made of carbon epoxy composite. And I cut an initial notch here and sharpen it with a razor blade used to shave yourself for men, okay? And again, the reason I have some dot here is just for a camera to pick up the deformation that called digital image coloration. You may know that. But basically, that will give the strain map of the whole deformation. But what you need to look at is just the crack. I load the specimen, just load it and unload it so that I can see the crack much clearly rather than just load it very quickly and you couldn't capture crack easily. So let's just look at the crack tip. Remember, it's load and unload. I load it and unload a bit, load it, unload it. You can see the crack growth. See that? And finally unload it. The crack is there. It's not going to recover. And this is another image when I do that X-ray CT scan, look at the crack tip. So you can see some zigzag pattern. But mostly the crack is uniform throughout the thickness. So this is the thickness throughout the page. Okay? When you color the crack here is colored this line, if you see from this direction. And some of the bridging happens because there are some little fibers bridging the crack for my specimen. And by doing that, you actually will measure each crack growth. You will measure a remote stress from your machine, and you convert that to your stress intensity factor. And I have measured like 10 different crack growths, and that is the delta A, the crack growth, and your fracture toughness. So that is the critical point when the cracks start to grow, and following that, they all crack until that point. And this plateau, you can use that as a fracture toughness value for your material. Okay? So now I kind of give you the brief understanding of the stress intensity factor and the fracture toughness. Let's look at some example. Before that, I still want to let's come back to the paper. Okay. Now you need to remember something. Okay. Okay. First thing to remember is the stress intensity factor for mode 1. That's what I have introduced, mostly mode 1. So we put that Ki. I means mode 1 fracture, open mode. It's Y times your sigma, let's say remote stress, times pi A. Okay? The crack length unit, megpa square root meter. Okay. But there's some other case for mode 2. For mode 2, let me draw mode 2 to you. So suppose we still have this central notched panel, and we apply a shear load now rather than a uniaxial load. Okay, that will be very similar. You have Y, but here, because we apply a shear stress, shear remotely. Okay, so that is shear stress pi A. As simple as that. Just change the stress here. That's mode 2. Mode 3, similarly, you have a tearing stress. And there's an example. So let's look at an example. Example 1, okay? We have a specimen. Loaded uniaxially sigma remote with a initial crack not perpendicular along that. So we have this typical. Let me just ask you questions. What's happened if I have a crack along the loading direction? I haven't shown any of that to you. In that case, did any crack happen? No, you're right. You can do any experiment yourself. So because basically mode 1 crack is you open the crack, but if you don't apply any load to open it, rather here is parallel to the crack. You're not open the crack. So there's no crack at all in this case. Okay? So there's no crack if initial notch is aligned with loading direction. Okay, now we do something more general. Example 2. In most of our daily life, the crack is not necessarily along to your perpendicular to your loading direction. Okay. What happens if you have a crack inclined to your loading direction? You again apply remote stress. We define a coordinate system. Let's put it here. The coordinate system should be, in general case here, x, y. So my question here, Ki. What is Ki for this case? What is K2 for this case? Okay? So think about this problem. The crack is inclined to your loading direction. We have an angle here. Let's write this angle beta. Yeah? So it seems a very different, a strange scenario, but when you think about the remote stress, it's so far away from the crack. And you can simplify this problem to look at that in a rotated stress, because you are more familiar with the stress. So this one is mode 1, one is this mode 2. This is the mode 1. You're familiar with both of these cases, right? They are directly, you can write the Ki equal to that equation, K2 equal to that equation. But for this case, you don't know, because you don't know the stress acting on that crack. So to do that, you need to rotate your stress such that your stress component now is along the crack orientation. Let's rotate the stress on that. So I haven't told you how to do that. So now let me give you the answer, how to do the stress rotation. Okay. So I'll give you the equation. So stress rotation or stress transformation. I just give you the direct answer, okay? Suppose I define C, a parameter equal to cosine beta and S equal to sine beta. Now I want to calculate the stress component in that rotated coordinate system, sigma x, sigma y. In a vector form, you can just simplify that. You don't need to write 2x. Okay. And shear stress, xy, y prime, okay, equal to a matrix. This is called rotation matrix, such that you can get the transformed stress, because you know you apply stress in this matrix, but you don't know that part, so you need the transformation matrix, which here is C squared, S squared. You don't need to remember that. In any of the case, I will give you this transformation matrix. Okay, here I just write that down so that we can do the calculation for it. SC C squared minus S squared. Okay, so what you need to do is just substitute these C and S into that rotation matrix. Then do that calculation, sigma xy times this line multiply that line. Okay, that's matrix calculation. So let's work out the answer. So what that means, let's write the sigma x prime, okay, equal to cosine beta square plus sigma y. So this term times that is sine beta square plus 2sc, so 2, and then this term times that, times tau xy shear stress, and times s and c. S is sine beta, c is cosine beta. Similarly, sigma y equal to this times that. So sigma x s squared, so sine beta squared, and plus sigma y cosine beta squared, and now minus 2 tau xy sine beta cosine beta, and tau x prime y prime equal to this times that. Okay, I will give you the simplified version. You can copy that down, but that's the simplified version of the linear algebra. Sine beta cosine beta plus tau xy cosine beta squared minus sine beta. Okay? So by doing that, now we can know the transformed stress in that coordinate system. And since what happens, our loading condition here is sigma x is 0 in the uniaxial loading case. So remember, x is in this direction, horizontal direction. So it's equal to 0. Sigma y is equal to the remote stress in that direction, vertical direction. And we didn't apply any shear stress. So this term equal to 0. So we substitute that into the equation. So let's say that whole term is equation 2. Equation 1, subs that into equation 1. So you get a simplified version. So that cancels out. Now you have sigma remote stress times sine beta squared. And this is equal to 0. Okay? And similarly, sigma y. We cancel that out, then you have this term left. And tau xy in transferred coordinate system is, so we cancel that part, and this only left sigma y. Sine beta cosine beta. Okay, so that's the transferred stress. So you just do some linear algebra, you get that. And now we can simplify our problem from this inclined crack. It can be equivalent to, okay, a crack Now we are looking at the crack in the transformed stage. So the crack, however, the coordinate system now is the transformed one. X prime, Y prime. Okay? We have rotated the stress tensor. And now when you look at that, you should write it sigma x. Sigma x. They are still remote. You could say in this coordinate system, they are still a remote stress. Plus, okay, there's some shear stress developed. So the crack here, and there's some shear stress. Again, you need to remind yourself you are in the coordinate system X and Y. And this is shear stress remote, okay? Equal to the term you calculated. Okay? Of course, you can also have some stress which the remote stress is applied parallel to a crack. Okay? So in that case, no crack propagation. Okay. So you can just cancel out this case. Just look at these two cases. Okay? X, Y. Right? So now it becomes much simplified version. So now the answer for the Ki. Ki now is, in this case, is we have a Y correction factor. Doesn't matter what the value for that. Now is just look at this case, remote stress, but in the transferred coordinate system, pi a, okay? This is still 2a, okay? And now what you need to do is just substitute your original stress into this equation. So that gives you sigma remote sine beta square. Oh, thank you. Pi a. Right? Understand? The key here is to work out the transformed stress. And then you put that result into the equation. You get that. Ki. K2 is y tau x y prime prime remote stress pi a. So similarly, you already work out that term. You put that inside, you plug in that inside. Sine beta, cosine beta, pi a. Okay? That's give you the answer. So I would say this is quite straightforward. The only thing important is do this stress transformation. And make sure you use this transformation matrix correctly, because beta is denoted here. But if you beta denote there, you need using a 90 degree minus that angle such that you get this angle, and plug that into this transformation matrix. Okay? Let's stop here.